Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Before the algorithms learned to anticipate questions, before relevance could be calculated in milliseconds, there existed a different kind of searching. It happened in the physical space of libraries, in the methodical progression through card catalogs, in the patient traversal of index pages that listed topics alphabetically but offered no guarantee of completeness. The search was linear, bounded by the limitations of human organization, dependent on someone having anticipated that a particular piece of information might someday be sought and having created a path to find it. What couldn't be anticipated remained unfindable, buried in the mass of accumulated knowledge, with no thread to guide the seeker. The frustration was quiet but pervasive. Researchers knew that somewhere in the vast collection of human writing, someone had likely explored their question, had conducted similar experiments, had reached conclusions that might illuminate or contradict their own thinking. But knowing that information existed somewhere was different from being able to locate it. The gap between the existence of knowledge and access to it could span years of effort or could never be bridged at all. Important discoveries were made and then remade by others who had no way to know the work had already been done. Insights languished in obscure journals that few would ever examine. The collective intelligence of humanity was fragmented, siloed in separate repositories with limited channels of connection. The problem intensified as the volume of recorded information grew. Each year brought more publications, more research papers, more documents of every kind. The traditional methods of organization, careful categorization, detailed indexing, systematic cataloging, struggled to keep pace. The work of organizing knowledge was itself a form of knowledge work, requiring expertise and judgment. Librarians and archivists devoted careers to creating finding aids, to building classification systems, to making collections navigable. Their work was essential, but couldn't scale infinitely. The ratio of documents to people who could organize them tilted steadily toward the documents. The transition from physical to digital storage initially seemed to promise a solution. Information stored as data could be searched directly, could be scanned for specific words or phrases without requiring human intermediaries to have created finding aids. Early digital databases allowed Boolean searches, combinations of terms that narrowed results through logical operations. This and that, this or that, this not that. The speed was impressive compared to manual searching. The comprehensiveness limited only by what had been digitized. But the interface between human questions and database queries remained awkward, requiring searchers to translate their needs into formal syntax to understand the logic of database operations. The mismatch between how people thought about questions and how computers could process them created its own friction. A person wondering about some topic didn't naturally think in terms of Boolean operators and exact phrase matching. They thought in natural language, in concepts and associations, in fuzzy approximations rather than precise specifications. The early systems demanded precision from users who often didn't know precisely what they were seeking, who were exploring rather than retrieving, who needed to discover what questions to ask as much as they needed answers. The limitation went deeper than interface design. Traditional organization schemes imposed hierarchies, required information to be placed in categories, to be classified according to systems that reflected assumptions about how knowledge was structured. A document about the intersection of two subjects had to be filed under one or the other, or duplicated, or referenced through cross-listings that required additional human effort to maintain. The rigidity of hierarchical organization meant that serendipitous discovery, finding something unexpected but relevant while searching for something else, depended on the categorizer and the seeker sharing similar mental models of how topics related to each other. The dream of comprehensive access to human knowledge had existed for centuries, expressed in various forms across different eras. The idea of a universal library, of collecting all books in one place, recurred throughout history, but always founded on practical limitations of space, preservation, and organization. Even if such a collection could be assembled, navigating it would require knowing what to look for, would require understanding the organizational scheme, would require time and patience that most seekers didn't possess. The fantasy of asking a question and receiving the answer, of frictionless access to accumulated wisdom, remained precisely that, a fantasy, constrained by the physical nature of books and the limited bandwidth of human attention. The digitization of text created new possibilities, but also new problems. As more documents became available in digital form, the challenge shifted from access to the physical objects toward access through the overwhelming quantity. A search that returned thousands of results was in some ways worse than a search that returned nothing. At least, nothing was definitive, while thousands of results created the burden of evaluation, of determining which among them were relevant, authoritative, useful. The problem wasn't scarcity, but abundance, not the absence of information, but the difficulty of distinguishing signal from noise. Different communities developed different approaches to this abundance. Academic databases implemented citation tracking, allowing searches based on which papers referenced which others, creating networks of intellectual connection. Specialized repositories for particular fields developed their own organization schemes, their own metadata standards, their own interfaces designed for domain-specific needs. But these solutions were fragmented, each serving a particular community, none providing comprehensive access across all domains of knowledge. The dream of universal access remained unfulfilled, replaced by a landscape of specialized tools that required expertise to navigate. The need wasn't just academic. As digital communication expanded, as more information of all kinds became available online, ordinary people encountered similar challenges in different contexts. Finding a specific piece of information, a recipe, a repair manual, a product review, required knowing where to look, which repository might contain it, what search terms might locate it. The web of interconnected documents grew faster than the tools to navigate it, creating a paradox where information was simultaneously more accessible than ever before and harder to find than when scarcity imposed natural limits. Business needs drove some innovation. Companies with large document collections needed employees to find information quickly. Technical specifications, previous correspondence, policy documents. The cost of employees spending hours searching for information that probably existed somewhere justified investment in better search tools. But enterprise search faced challenges similar to web search: heterogeneous document types, inconsistent metadata, the difficulty of understanding what a user actually wanted when they entered a query that might be ambiguous, might use terminology differently than the documents used, might be based on incomplete or incorrect assumptions about what information existed. The underlying challenge was one of meaning and relevance. Computers could match text strings efficiently, could find exact phrases or word combinations across vast collections nearly instantly. But understanding what a document was about, determining whether it would actually help answer a particular question, required interpretation that seemed to require human judgment. The semantic gap between the literal content of documents and what they meant, between what a query literally asked for and what the searcher actually needed, appeared to be a fundamental barrier to truly effective automated search. Yet the need was undeniable. The volume of human knowledge continued to grow exponentially. The rate of new document creation accelerated. The cost of failing to find existing information in duplicated effort, in missed insights, in opportunities lost, became increasingly significant. Something had to change. Some new approach had to emerge that could help people navigate the flood of information more effectively than the methods inherited from earlier eras of scarcity and physical constraints. The first attempts to organize digital information drew heavily from traditions developed for physical collections. The metaphors were familiar: directories that worked like filing cabinets, hierarchical structures that mirrored the way libraries organized books by subject. Early networks of connected computers used these approaches, creating categorized lists of resources, indexes maintained by hand that pointed to where specific types of information could be found. The work was manual, curatorial, dependent on individuals who understood both the available resources and how people might want to access them. Some services emerged that attempted to catalog the growing collection of online resources. Teams of human editors reviewed sites, assigned them to categories, wrote brief descriptions of their contents. The result was browsable directories, taxonomies of knowledge that users could navigate by drilling down through increasingly specific categories. Looking for information about a particular topic meant starting broad, perhaps selecting a category like science or arts, then narrowing through subcategories until reaching a manageable list of resources that might be relevant. The approach scaled poorly, requiring editorial work that grew linearly with the number of resources to be catalogued, but it provided a human-curated entry point that many found more approachable than attempting unstructured search. Automated approaches explored different principles. If the goal was to find documents relevant to a query, perhaps the solution was to analyze the documents themselves, to build indices that captured not just what words they contained, but patterns of word usage, frequencies, co-occurrences. Early systems created inverted indices, data structures that listed for each word which documents contained it and where within those documents it appeared. This allowed rapid lookup, converting a search query into a list of documents containing the specified terms. But simply finding documents that contained certain words didn't solve the relevance problem. Many documents might contain a word without being meaningfully about the concept that word represented. The challenge of determining relevance drove innovation in ranking approaches. Not all documents containing a search term were equally useful, so systems needed ways to order results, to present the most likely to be relevant documents first. Early ranking algorithms used simple metrics. How many times did the search terms appear? Did they appear in the title or just the body text? How long was the document? These heuristics captured some signal about relevance, but were crude, easily fooled by documents that simply repeated terms many times or that used them in headings without substantial discussion. Citation analysis offered a different approach to determining importance. In academic contexts, papers that were cited frequently by other papers were generally more significant than those rarely cited. This suggested that the link structure, the network of references between documents, contained information about authority and relevance beyond what existed in the document's content alone. A document might not explicitly claim to be important, but if many other documents referenced it, that collective judgment provided evidence of significance. The challenge was applying this insight to contexts beyond formal citation networks, to the broader web of interconnected documents where links existed for many reasons beyond scholarly reference. The concept of link analysis as a ranking signal emerged from thinking about how authority propagated through networks. If important documents linked to other documents, perhaps those linked documents inherited some measure of importance from the association. This created the possibility of recursive definitions. A document was important if important documents linked to it, and those documents were themselves important based on what linked to them. The circularity seemed problematic, but actually pointed toward mathematical frameworks for calculating importance across entire networks simultaneously. The mathematical approach to link analysis borrowed from older ideas about how networks propagated influence. The principle was similar to academic citation networks, but applicable to any set of interconnected documents. Each link could be thought of as a vote of confidence, an assertion by the linking document that the linked document was relevant or authoritative on some topic. But not all votes should count equally. A link from an authoritative source should matter more than a link from an obscure page. This suggested an iterative calculation where authority was distributed through the network based on the existing distribution of authority, continuing until the values stabilized. The insight enabled a kind of global analysis that previous search approaches lacked. Instead of examining each document in isolation, calculating its relevance based solely on its own properties, link analysis considered documents in context, understanding them through their relationships to other documents. This captured something important about how knowledge actually worked. Understanding a document often required understanding its intellectual lineage, where it fit in ongoing conversations, what other work it built upon or responded to. Text analysis continued to evolve in parallel. Simple word matching gave way to more sophisticated linguistic analysis. Systems began to understand synonyms, to recognize that different words might represent the same concept, that queries phrased in various ways might be seeking the same information. Stemming algorithms reduced words to their root forms so that searching for running would also match documents about run and runner. These improvements reduced the brittleness of exact text matching, made the systems more forgiving of variations in how queries and documents expressed concepts. The challenge of understanding user intent became increasingly central. The same query might mean different things to different users, or even to the same user in different contexts. Someone searching for Java might want information about the programming language, the island, or coffee. Disambiguation required understanding context, previous searches, location, patterns in how the query was phrased. Early systems had no such context, treating each query as an isolated event, forcing users to add clarifying terms if the first results didn't match their intent. Relevance feedback emerged as a technique for refining search results through interaction. If a user indicated that certain results were helpful or unhelpful, the system could use that feedback to adjust the ranking, to learn what characteristics distinguished good results from poor ones for that particular query. This interactive refinement moved search from a single transaction, query in, results out, toward a conversation, a process of iterative clarification where the system learned what the user actually wanted through observation of their behavior. The concept of personalization suggested that search results should vary based on who was searching. Two users with different backgrounds, different expertise levels, different reasons for searching might benefit from different rankings of the same underlying set of results. An expert and a novice, searching for the same term, likely wanted different types of information. The expert might seek cutting-edge research, while the novice needed basic explanations. Implementing personalization required building models of users, understanding their characteristics and preferences, raising questions about privacy and the appropriateness of tailoring information access. Spam emerged as a problem almost as soon as automated ranking became important. If appearing high in search results had value, attracting visitors, establishing credibility, generating revenue, then incentives existed to manipulate the ranking algorithms. Early manipulation techniques were crude, repeating keywords excessively, hiding text from human viewers while making it visible to search engines, creating artificial link structures designed to inflate importance scores. The arms race between ranking algorithms and those trying to manipulate them became a defining feature of search development. The technical challenges of scale grew alongside the conceptual challenges of relevance. As the amount of indexed information increased, the computational requirements for processing queries and calculating rankings escalated. Responding to searches in reasonable time required distributed systems, parallel processing, careful optimization of data structures and algorithms. The infrastructure needed to support search at scale became its own domain of innovation, distinct from but interrelated with the challenges of determining what results to return. The breakthrough came not from a single innovation, but from the convergence of several ideas that had been developing in parallel. The insight that link structure could reveal authority, combined with efficient algorithms for calculating importance across vast networks, combined with increasingly sophisticated text analysis, created the foundation for something qualitatively different from what had existed before. The implementation was elegant in its core concept. Treat the web as a democracy where pages voted for other pages through links, but weight those votes by the authority of the voting page, creating a recursive measure of importance. The mathematical foundation rested on linear algebra, on treating the web as a massive matrix where each entry represented the strength of connection between pages. The problem of calculating authority became a problem of finding eigenvectors, of determining stable distributions of importance across the network. The computation was intensive, requiring processing of the entire web to calculate rankings. But once calculated, those rankings could be used to order search results, placing authoritative pages ahead of obscure ones when both contained the query terms. The algorithm's elegance lay in its resistance to simple manipulation, creating pages that linked to each other to inflate importance didn't work if those pages themselves had no incoming links from authoritative sources. The global calculation meant that importance had to come from somewhere legitimate in the existing network. You couldn't bootstrap authority from nothing. This made the system more robust against spam than approaches that looked only at local features of pages, though it didn't eliminate manipulation entirely, just made it harder and more expensive. Early implementations ran on modest hardware, processing a fraction of the total web, updating rankings periodically rather than continuously. The results were imperfect, but noticeably better than alternatives. Queries that previously returned loosely relevant results, scattered among noise, now surfaced authoritative sources at the top of the list. The improvement wasn't universal. For some queries, the older approaches worked fine, but for enough searches, the difference was significant enough to attract users who noticed that one particular search service consistently returned better results than competitors. The system launched quietly, without extensive promotion, relying initially on word of mouth from early users who appreciated the result quality. The interface was minimal, deliberately sparse, just a search box and results, no clutter of categories or directory listings. This simplicity was partly aesthetic choice and partly necessity, reflecting the automated nature of the system that didn't require human editors to maintain category hierarchies. The focus on pure search, unadorned by other features, became a defining characteristic. Growth was exponential in the early period. Users who found the service useful told others. Each new user represented potential queries that provided data about what people searched for, which results they clicked on, what patterns of usage revealed about relevance. This data fed back into improvements, creating a virtuous cycle where better results attracted more users whose behavior generated data that enabled further improvements. The network effect wasn't just about users, but about the feedback loop between usage and quality. The index grew rapidly as more resources were devoted to crawling and processing the web. Automated programs traversed the network of pages, following links, downloading content, extracting text and link structure. The crawling process was never complete. New pages appeared constantly, existing pages changed, links were added and removed. The system had to continuously recrawl, updating its understanding of the web's structure and content. The logistics of this continuous indexing required sophisticated infrastructure, systems for managing the flow of data from crawlers through processing pipelines to searchable indices. The ranking algorithm evolved through continuous refinement. The core principle of link analysis remained, but dozens of additional signals were incorporated. How recently was a page updated? How did the query terms appear in the page's URL or title? What was the reading level of the content? Did the page load quickly or slowly? Each signal contributed marginally to the overall ranking, the combination creating more nuanced judgments of relevance than any single factor could provide. The weighting of these signals was adjusted constantly through experimentation, through analysis of which changes improved result quality as measured by user behavior. Machine learning entered the picture gradually, first for specific subtasks, then more broadly. Training algorithms on examples of good and poor results for queries allowed the system to discover patterns that human engineers might not notice, to find combinations of signals that predicted relevance better than hand-tuned heuristics. The challenge was obtaining training data, reliable judgments of which results were good for which queries. Some came from manual evaluation, human raters examining results and scoring their quality. More came from implicit signals in user behavior, which results were clicked, how long users spent on pages after clicking, whether they returned to search results or seemed satisfied. The accumulation of data became a strategic asset. The more searches processed, the more examples of queries and user responses, the better the system could learn to distinguish relevant from irrelevant results. This created a barrier to entry for potential competitors. Building a comparably good search engine required not just implementing algorithms, but accumulating similar quantities of usage data to train those algorithms effectively. The technical challenge was surmountable, but the data advantage compounded over time. Personalization became more sophisticated as the system learned to maintain context across searches. Queries didn't happen in isolation, but in sequences, in sessions where users refined their information needs through multiple iterations. Understanding these patterns allowed the system to interpret ambiguous queries based on what the user had searched for previously, to recognize when someone was continuing an investigation versus starting a completely new topic. The continuity of search sessions revealed intent more clearly than individual queries in isolation. Geographic signals provided another dimension of personalization. A query for a common business type probably wanted local results. Someone searching for restaurants likely wanted nearby options, not an academic discussion of restaurant economics. Determining location from network addresses allowed the system to prioritize geographically relevant results for queries where location mattered. This made search more useful for everyday practical needs, not just for abstract information seeking. The infrastructure scaled through distributed computing, spreading the computational work across thousands of machines working in parallel. No single computer could store the entire index or process the query volume, so the work was partitioned with different machines responsible for different portions of the index. Queries were routed to appropriate machines. Results collected and merged. Rankings calculated by aggregating information from across the distributed system. The engineering challenge was ensuring consistency and speed despite this distribution, ensuring that queries completed in fractions of a second, even though they required coordination across many machines. Crawling the web became an increasingly complex operation. The total number of pages numbered in the billions, growing constantly. Some pages changed frequently, requiring regular recrawling, while others remained static and needed less frequent updates. Determining optimal crawl frequencies for different pages required balancing freshness against the computational cost of crawling. Politeness constraints limited how aggressively crawlers could request pages from individual sites to avoid overwhelming servers or wasting bandwidth. The crawling system had to respect robots.txt files where site operators specified which parts of their sites should or shouldn't be indexed. The accumulation wasn't just technical, but cultural. search became a verb, a default action when seeking information. The behavior of formulating a query, examining results, refining the search if initial results were inadequate, became habitual for hundreds of millions of people. This cultural shift meant that the patterns of information seeking changed. Instead of carefully considering where information might be before beginning to look, people could simply search and see what appeared. The reduced friction of finding information enabled different approaches to learning and investigation, less systematic but more exploratory. The machinery of search operated on a scale difficult to comprehend. Data centers housed tens of thousands of servers, each a metal box filled with processors, memory, storage drives. The servers were arranged in racks, the racks in rows, the rows in buildings specifically designed to manage heat, provide redundant power, enable rapid replacement of failed components. The hum of cooling systems was constant, moving air across processors that generated heat as they performed calculations, across hard drives whose spinning platters generated friction, across network switches that routed data between machines. The physical infrastructure reflected careful optimization of countless details. The spacing between racks balanced density against cooling efficiency. The design of power distribution minimized energy loss. The network topology ensured that any machine could communicate with any other through multiple paths, so that individual link failures didn't isolate parts of the system. Even the colors of the buildings in some locations were chosen to reflect sunlight, reducing cooling loads in warm climates. The mundane physical details mattered because at this scale, small inefficiencies multiplied into significant costs. Crawling was continuous, mechanical, relentless. Hundreds of thousands of threads of execution ran simultaneously across the distributed system, each managing connections to web servers, requesting pages, downloading content. The crawlers maintained politeness, waiting between requests to the same server, respecting rate limits, honoring requests not to crawl certain sections. But collectively, they represented an enormous load, a significant fraction of total web traffic. Automated programs requesting billions of pages per day to keep the index current. The downloaded content flowed through processing pipelines. Text was extracted from HTML, JavaScript, PDF files, document formats of every kind. The extraction process had to handle malformed markup, unexpected encodings, attempts to hide or obfuscate content. Once extracted, the text was analyzed, tokenized into words, reduced to root forms, analyzed for language. Links were extracted and normalized, tracking which pages pointed to which others. The metadata about pages, when they were last modified, how large they were, what server headers indicated about their content, was captured alongside the text and link structure. Indexing transformed the processed content into searchable data structures. The inverted index mapped each word to the list of documents containing it, along with positional information about where in those documents the word appeared. This data structure enabled rapid lookup during query processing. Given a set of query terms, the system could quickly identify documents containing all of them, could examine how the terms appeared relative to each other, could calculate relevance scores based on term frequencies and positions. Building and maintaining the index required enormous storage and careful compression to keep the data size manageable. The link graph, the complete network of connections between pages, was processed separately to calculate importance scores. This calculation had to consider the entire graph simultaneously, had to iterate until values stabilized, had to handle special cases like disconnected components and rank sinks where importance could drain away. The computation ran periodically, taking hours or days to process the complete graph, producing updated importance scores that were then merged into the main index. Query processing happened in milliseconds, but involved orchestrating work across hundreds of machines. When a query arrived, it was parsed and analyzed, corrected for common misspellings, expanded with synonyms, classified by type and likely intent. The processed query was then sent to index servers, which identified candidate results, pages containing the query terms with appropriate frequency and positioning. These candidates were scored using the combination of relevant signals, ranked and returned. The scoring calculation accessed many different data stores simultaneously. The text relevance signals came from the inverted index. Important scores came from the link analysis database. Freshness information came from crawl metadata. Quality signals came from systems that analyzed page characteristics. Geographic relevance required location databases. Each piece of information had to be retrieved, integrated, and weighted appropriately, all within the time budget for query processing. The mechanical coordination of these distributed data accesses was as important as the algorithms for calculating relevance. Caching reduced the computational load for repeated queries. Popular searches occurred frequently, and storing their results meant that subsequent instances of the same query could be served from cache rather than recalculated. The cache management itself required sophistication, determining which results to cache, how long to keep them before refreshing, how to balance hit rates against memory consumption. The caching infrastructure spanned multiple layers, from local caches on individual servers to distributed caching systems shared across data centers. Load balancing distributed queries across available servers, preventing any single machine from being overwhelmed. The distribution had to account for machine capacity, current load, network topology. If certain servers failed or became unavailable, their load needed to shift smoothly to others without disrupting service. The mechanical problem of maintaining responsiveness despite constant component failures drove sophisticated monitoring and routing systems that could detect problems and adapt automatically. Data replication ensured reliability despite hardware failures. Every piece of information existed in multiple copies across different machines, different racks, sometimes different physical locations. When drives failed, and they failed constantly at this scale, the data they contained was already available elsewhere. The replication system monitored for failures, created new copies to maintain redundancy levels, distributed data across the infrastructure to prevent any single failure point from being critical. The mechanics of this continuous replication, checking, and rebalancing operated invisibly but were essential to reliability. Network infrastructure connected the distributed components. High bandwidth links moved data between servers, between data centers, between continents. The network topology was designed for redundancy and performance, with multiple paths between any 2 points, automatic routing around failures, careful management of bandwidth to prevent congestion. The physical reality of network cables, fiber optic lines, routing equipment formed the substrate on which the logical operations of search depended. Energy consumption was substantial and growing. Each server drew power continuously, converted much of it to heat that had to be removed through cooling systems that themselves consumed energy. The total power consumption of the infrastructure, measured in megawatts, comparable to small cities. This prompted attention to efficiency, more efficient processors, better power supplies, cooling designs that used outside air when possible, rather than mechanical refrigeration. The mechanical challenge of operating at this scale with acceptable energy costs drove innovation in hardware design and data center architecture. Storage systems managed petabytes of data across thousands of drives. The drives were organized into redundant arrays with sophisticated error correction and recovery mechanisms. The storage wasn't static. The index was constantly being updated as pages were recrawled, as new pages were discovered, as old pages disappeared. Managing the writes, maintaining consistency, ensuring that queries saw coherent snapshots of the index, even as updates proceeded, required careful coordination and mechanical precision in how data was written and read from spinning platters or flash memory. The machinery operated continuously, without pause for maintenance or rest. Components were replaced while the system ran, hot-swapping failed drives, rotating out servers for upgrades, expanding capacity by adding new racks. The mechanical dance of keeping the infrastructure operational while it processed billions of queries per day required careful choreography, automated monitoring that could detect problems before they became critical, processes for gracefully removing capacity for maintenance without impacting users. As search became essential infrastructure, patterns of use crystallized into conventions that shaped how information was created and organized. Website operators learned that certain practices made their content more discoverable: descriptive titles, clear hierarchical structure, meaningful link text. These weren't requirements enforced by the search system, but empirical discoveries about what worked, what helped pages rank well for relevant queries. The accumulated wisdom became informal standards, best practices shared through documentation and discussion. The concept of optimization emerged as website operators sought to improve their visibility in search results. Understanding how the ranking algorithms worked, or attempting to understand, since the details were proprietary and constantly evolving, allowed for deliberate choices about how to structure content, which words to emphasize, how to build link profiles. The line between optimization and manipulation was fuzzy, with legitimate practices aimed at clarity and accessibility, shading into attempts to game the system through artificial inflation of ranking signals. Guidelines developed to distinguish acceptable from unacceptable practices. Search providers published recommendations for webmasters explaining which techniques would help pages rank appropriately and which might result in penalties or removal from the index. Clear content that matched user intent was encouraged. Hidden text, keyword stuffing, artificial link schemes were forbidden. The enforcement was imperfect. Detection of violations required continuous evolution of algorithms to identify suspicious patterns. But the existence of published standards established norms about appropriate behavior. Structured data emerged as a standardization effort that bridged human-readable content and machine processing. Markup languages allowed content creators to explicitly indicate what different pieces of information represented. This text was a product name. This number was a price. This date was an event time. The structured annotations didn't change how the content appeared to human readers, but provided explicit signals to search systems about the semantic meaning of page elements. This enabled richer search results that could display specific information directly rather than just links to pages. The standardization of robots.txt files created a protocol for site operators to indicate which parts of their sites should or shouldn't be crawled. The standard was simple: a text file in a standard location, specifying path patterns to exclude from crawling. Crawlers checked this file before accessing other content, respecting the specified boundaries. The protocol was entirely voluntary, enforced only through convention and the enlightened self-interest of crawler operators who understood that respecting site operators' wishes was necessary for the ecosystem to function. Sitemaps provided the complement to robots.txt. Rather than specifying what not to crawl, they explicitly listed what should be crawled. Site operators could generate files listing all their pages, indicating update frequencies and priorities, helping crawlers discover content that might not be easily reachable through following links. The sitemap standard specified the format and location of these files, creating interoperability between different search systems and different types of websites. The search interface itself became standardized through widespread adoption of common patterns. The single search box, the list of results with titles and snippets, the pagination controls, these elements appeared consistently across different search implementations, creating user expectations about how search should work. The standardization wasn't enforced by any authority, but emerged through imitation of successful patterns and users' learned behaviors that made deviation costly in terms of usability. Query syntax developed informal standards around special operators for refining searches, quote marks for exact phrase matching, minus signs for exclusion, site-specific searches, date range filters. These capabilities existed in most search implementations with similar syntax. Users learned these operators and expected them to work consistently, creating pressure for new search systems to adopt compatible syntax even if their underlying implementations differed. Results presentation gradually standardized around certain conventions for different query types. Informational queries showed traditional blue links with descriptions. Navigational queries attempting to reach a specific site surfaced that site prominently. Transactional queries related to commerce might display product information and prices. The differentiation of result types based on inferred intent became a standard approach, though implementations varied in sophistication. Advertising integration followed patterns that balanced revenue generation with user experience. The separation of paid results from organic results through visual distinction and labeling became standard practice, establishing trust that users could distinguish promoted content from algorithmically ranked results. The placement of ads, typically above or beside organic results, followed conventions that maximized visibility while maintaining clear boundaries. The standardization helped users develop mental models for interpreting search results pages. Privacy practices around search data gradually standardized, though with significant variation between providers. The recognition that search queries could reveal sensitive information about users' interests, health conditions, financial situations, led to policies about data retention, anonymization, and use limitations. Some providers committed to not retaining query logs beyond specific periods, to anonymizing data before analysis, to not linking search history to personal identities. Others retained more data for longer periods, trading privacy for improved personalization and service quality. The variation reflected different philosophical positions about the appropriate balance. Ranking signal standardization happened implicitly through the convergence of different systems towards similar approaches. The importance of link analysis, page loading speed, mobile compatibility, secure connections. These factors became important across multiple search implementations, not through coordination, but through independent discovery of what signals actually predicted result quality. The convergence suggested that certain properties were genuinely important for relevance, not just artifacts of particular algorithmic choices. International standards developed around how search handled different languages and scripts. Character encoding standards allowed proper handling of text in any writing system. Language detection algorithms identified page languages to enable appropriate processing and matching to query languages. Translation integration allowed queries in one language to find results in others, breaking down linguistic barriers to information access. The technical standards for representing and processing multilingual content became essential infrastructure. Accessibility standards ensured that search interfaces could be used by people with disabilities. Keyboard navigation support, screen reader compatibility, sufficient contrast for visual elements. These practices made search accessible to users with various impairments. The standards weren't unique to search, but the adoption of web accessibility guidelines in search interfaces helped establish expectations that essential services should be usable by everyone. The mobile era brought new standardization around responsive design and mobile-friendly content. As search shifted from desktop to mobile devices, the ranking algorithms began preferring pages that worked well on smaller screens, that loaded quickly on cellular connections, that didn't require zooming or horizontal scrolling. This created strong incentives for site operators to adopt mobile-friendly designs, effectively standardizing much of the web around mobile-first approaches. The search ranking preferences amplified what was already a technological shift, accelerating adoption of standards for responsive, mobile-compatible content. The moment when search became indispensable wasn't marked by any particular event. It happened gradually, through the accumulation of small dependencies, through the slow integration of search into daily routines, until its absence became unthinkable. People stopped trying to remember where they had read something or what a website's exact address was, confident they could search and find it again. The mental habit of memorization gave way to the habit of retrieval, of knowing that information could be located when needed, rather than storing it internally. The transition altered how knowledge work happened. Researchers no longer needed to maintain extensive personal libraries or comprehensive knowledge of their field's literature. They could search, could discover relevant work on demand, could follow chains of citations backward and forward through time. The change freed cognitive resources from remembering where information lived, allowing focus on synthesis and analysis instead. But it also created dependence. When search was unavailable, either through technical failure or deliberate restriction, the ability to function effectively diminished noticeably. Education transformed silently as students grew up with ubiquitous search access. The skills of finding information in libraries, of navigating card catalogs and reference works, became less central to academic training. New literacies emerged around evaluating search results, distinguishing authoritative from unreliable sources, formulating effective queries. The transition wasn't universally positive. Some worried about the depth of understanding that came from systematic reading versus the breadth that came from search-driven exploration. But the change was largely irreversible, reflecting the reality that information abundance required different skills than information scarcity. Professional practice across many fields incorporated search as essential infrastructure. Medical professionals consulted symptoms and treatments during patient consultations. Lawyers researched case law and precedents throughout their daily work. Journalists verified facts and found sources through search. Technical workers looked up programming syntax and troubleshooting steps continuously. The integration was so complete that removing search access would disable significant portions of professional capability, not immediately, but within hours, as the limits of unaided memory became apparent. The geographic implications unfolded quietly. Access to search required internet connectivity, creating new dimensions of inequality between connected and unconnected populations. Those with reliable access gained enormous informational advantages over those without, advantages that compounded over time as more resources and services assumed universal search availability. The digital divide wasn't just about connectivity, but about access to the infrastructure of information retrieval that search represented. Commercial behavior shifted as businesses recognized that search visibility directly impacted revenue. Being discoverable for relevant queries became a business necessity, not an optional enhancement. Entire industries emerged around optimization, around advertising through search, around analyzing search data to understand market trends and consumer interests. The silent transition made search platforms into gatekeepers, not through intentional control, but through the practical reality that invisibility in search results meant near invisibility in the market. Personal memory outsourcing became a widespread phenomenon. People stopped trying to remember phone numbers, addresses, facts that could be quickly searched. This freed mental resources, but also created a different relationship with knowledge, more fluid, more accessible, but perhaps less deeply internalized. The debate about whether this represented cognitive enhancement or atrophy remained unresolved, with evidence supporting both perspectives depending on what aspects of cognition were measured. The transition affected social dynamics in subtle ways. Arguments about factual questions could be quickly resolved through search, changing the nature of disagreement toward interpretation rather than facts themselves. Expertise became less about knowing information and more about knowing how to find, evaluate, and synthesize it. The authority of those who simply knew many facts diminished relative to those who could efficiently navigate information resources. Cultural memory, preserved through search, operated differently than memory stored in human minds or physical archives. The complete searchability of digitized information meant that nothing was truly forgotten as long as it remained indexed. Old writings, photographs, records that would have been practically inaccessible in physical archives became instantly discoverable. This created new forms of accountability. Past statements and actions could be found and resurfaced, but also new challenges around the right to be forgotten, around whether everything should remain perpetually accessible. The transition made certain business models obsolete. Print encyclopedias, phone directories, classified advertising, all faced existential challenges from the availability of searchable alternatives that were more current, more convenient, and often free to access. The economic disruption happened gradually, but was ultimately complete, demonstrating that search wasn't just an additional option, but a replacement for previous information infrastructure. Behavior became measurable in new ways, as search queries revealed aggregate interests, concerns, and intentions. Public health officials could track disease outbreaks through search patterns. Economists could gauge consumer confidence through searches for particular products or financial terms. Political campaigns could understand voter priorities through the questions people asked. The transition made previously invisible patterns of human interest and behavior suddenly legible through the traces left in search logs. The silent transition included a shift in information authority. Traditional gatekeepers, publishers, librarians, editors who decided what information would be widely available, lost some influence relative to algorithms that determined what appeared in search results. The algorithmic curation operated by different principles than human curation, prioritizing different signals, responding to different incentives. The transition wasn't absolute. Human judgment still shaped much of what was published and how it was structured. But the balance shifted. Search changed the economics of attention. With virtually unlimited information accessible through search, the scarce resource became human attention rather than information availability. This shifted value toward the mechanisms for filtering and surfacing relevant information from the vast available corpus. The platforms that could most effectively capture and direct attention gained enormous economic power, not through controlling information, but through controlling its discoverability. Privacy implications of the transition became apparent only gradually. The accumulation of search histories created detailed profiles of individual interests, concerns, questions. These profiles revealed information people might not consciously share: health anxieties, financial stress, relationship problems, political leanings. The data's sensitivity wasn't obvious in individual queries, but emerged from patterns across many searches over time. The transition to search dependence was also a transition to surveillance, though the surveillance was often invisible and its implications not immediately clear. The transition altered the relationship between remembering and forgetting. In previous eras, most information was effectively lost over time, accessible only with great effort, if at all. Search made historical information perpetually present, collapsing temporal distance. Yesterday's news was as searchable as today's. Last decade's writings remained as accessible as last week's. This created a kind of eternal present, where temporal context flattened, where understanding that information came from a particular moment required effort rather than being implicit in the difficulty of accessing it. Behind the visible interface of search results lay layers of infrastructure built to operate at planetary scale. The systems that enabled queries to be answered in fractions of a second existed in hundreds of locations simultaneously, distributed across continents, coordinated through protocols that made the geographical dispersion invisible to users. The infrastructure wasn't monolithic, but rather an ecosystem of specialized components, each optimized for particular functions. all working together to transform queries into results. Content delivery networks form the outermost layer, caching frequently accessed data close to users geographically. When someone searched, their query could be processed by servers in their region rather than traveling to a central location. The response time savings were measured in milliseconds, but those milliseconds mattered for user experience and for the volume of queries that could be processed. The distributed architecture also provided resilience. If servers in one region failed, queries could be routed to others without users noticing the disruption. The crawling infrastructure operated continuously, discovering and downloading content from across the web. The crawlers had to be polite, respecting rate limits and access restrictions, while being thorough enough to maintain current indices of billions of pages. The logistics were substantial, determining optimal crawl schedules for different types of content, managing the bandwidth consumption, handling the variety of document formats and encodings. The crawler infrastructure was separate from query processing, operating on different timescales, but feeding the data that made search possible. Processing pipelines transformed raw downloaded content into searchable indices. The pipelines were designed for throughput, processing millions of documents per day, extracting text and metadata, analyzing content quality, calculating initial relevant signals. The processing happened in stages, with each stage feeding the next. The whole pipeline architected to handle the continuous flow of new and updated content without bottlenecks. Failures in processing. Individual documents couldn't stall the entire pipeline, requiring error handling and recovery mechanisms at each stage. Storage infrastructure managed the massive databases that held the searchable indices, the link graphs, the various signals used in ranking. The storage systems were distributed and redundant, using techniques like sharding to partition data across many machines and replication to ensure availability despite hardware failures. The data structures were optimized for the specific access patterns of search, rapid lookups, efficient updates, the ability to process queries that might touch many parts of the index simultaneously. Index serving infrastructure handled the real-time query processing, receiving past queries, and returning ranked results. The serving systems accessed the stored indices, retrieving candidate documents, calculating relevant scores, applying personalization and filtering. The work was parallelized across many machines, with sophisticated load balancing to ensure even distribution of work and consistent response times. The serving infrastructure had to scale elastically, handling quiet periods and peak load without degrading performance or wasting resources during low utilization. Machine learning infrastructure trained and deployed the models that powered many aspects of ranking and understanding. The training systems processed enormous datasets of queries and user interactions, adjusting model parameters to improve predictions of relevance. The training happened offline, taking hours or days to complete, producing models that were then deployed to the serving infrastructure where they could be applied in milliseconds to individual queries. The infrastructure for managing this machine learning lifecycle, training, evaluation, deployment, monitoring, became as important as the models themselves. Monitoring systems provided visibility into the health and performance of all components. Metrics about query latency, error rates, resource utilization, result quality were collected continuously from across the distributed infrastructure. The monitoring had to operate at scale, processing telemetry from thousands of machines, identifying anomalies and degradation patterns, alerting engineers when problems required intervention. The monitoring infrastructure was itself substantial, a meta-system observing the primary systems. Experimentation infrastructure enabled continuous testing of improvements. Changes to algorithms, to ranking signals, to interface elements were tested on subsets of traffic, measuring their impact on metrics like user satisfaction, query refinement rates, time to success. The infrastructure managed the complexity of running many experiments simultaneously, ensuring clean measurements despite overlapping tests, making statistical analysis of results routine. The ability to experiment safely and measure outcomes became a competitive advantage, enabling rapid iteration on improvements. The advertising infrastructure operated alongside the organic search systems, with its own indices, its own auction mechanisms, its own serving infrastructure. The ads had to be selected and ranked in real time based on the query, on advertiser bids and budgets, on predicted click-through rates and conversion probabilities. The computational challenge was substantial. Millions of advertisers with billions of keywords and ad variations, all needing to be considered for each query in milliseconds. The advertising infrastructure was often larger and more complex than the organic search infrastructure it accompanied. Network infrastructure connected all the components with carefully designed topologies to minimize latency and maximize bandwidth. The internal networks use specialized protocols optimized for the specific communication patterns of distributed search systems. The external networks connected data centers to the internet, with routing designed to ensure queries reach the nearest available serving location. Network capacity planning had to anticipate growth, ensuring that infrastructure could handle increasing query volumes without congestion becoming a bottleneck. Power infrastructure designed for reliability and efficiency supplied electricity to the thousands of servers. Redundant power supplies, backup generators, battery systems ensured continuous operation despite utility outages. The engineering focused on power usage effectiveness, on minimizing the overhead of power conversion, and cooling relative to the power consumed by the computational work itself. The infrastructure included smart power distribution that could shed non-critical loads during emergencies, prioritizing query serving over background processing. Cooling systems removed the heat generated by dense concentrations of computing equipment. The designs ranged from traditional air conditioning to more exotic approaches like direct liquid cooling or using outside air when ambient temperatures permitted. The thermal management had to handle hotspots, local areas where equipment concentration or airflow patterns created higher temperatures. The cooling infrastructure represented a significant fraction of total energy consumption, making efficiency improvements in cooling almost as valuable as improvements in computational efficiency. Security infrastructure protected against various threats: unauthorized access, denial of service attacks, data breaches. Multiple layers of defense included network perimeter security, authentication and authorization systems, encryption of data in transit and at rest, anomaly detection systems that identified suspicious patterns. The security infrastructure had to be thorough without significantly impacting performance, implementing checks and protections that operated efficiently at scale. Development and deployment infrastructure enabled engineers to build, test, and release changes to the systems safely. Version control systems tracked code changes. Automated testing verified functionality. Continuous integration systems built and validated changes. Deployment systems gradually rolled out updates, monitoring for problems and automatically rolling back if issues were detected. The infrastructure for managing the life cycle of the search system itself became a significant engineering challenge, requiring tools and processes that worked at the scale and complexity of the primary system. The infrastructure of search operated without regard to national boundaries, yet existed entirely within them. Data centers sat in specific jurisdictions, subject to local laws. Network cables crossed borders, creating dependencies on international agreements and infrastructure. Users accessed search from everywhere, their queries routed through systems that might traverse multiple countries between submission and response. The technical borderlessness of the network confronted the legal and political reality of territorial sovereignty, creating tensions that had no simple resolution. Language presented both barrier and bridge. Search systems had to understand queries in hundreds of languages, match them to content in appropriate languages, sometimes bridge between languages through translation. The infrastructure for language detection, for maintaining indices organized by language, for understanding linguistic variations and dialects, became essential to global functionality. The dominance of English in technical documentation and much online content created asymmetries. English speakers could find more information more easily than speakers of less represented languages. Cultural differences shaped how search was used and what it was used for. In some regions, search was primarily a navigation tool, a way to reach known websites. In others, it was predominantly for information seeking or commercial research. The variations reflected differences in internet maturity, in device access patterns, in cultural norms about information gathering. The infrastructure had to accommodate these differences, adapting result types and ranking signals to match local usage patterns while maintaining global consistency in core functionality. Economic disparities manifested in the infrastructure's distribution. Data centers concentrated in regions with abundant electricity reliable connectivity, political stability, and favorable economic conditions. This geographic clustering created latency differences. Users near major data centers experienced faster responses than those in remote regions. The infrastructure gradually expanded to serve underserved regions, but economics limited how evenly distributed the physical infrastructure could be. Regulatory fragmentation required the infrastructure to operate differently in different jurisdictions. Some countries required data to be stored locally, necessitating regional data centers and modified data flows. Others imposed requirements about content filtering, about data retention, about government access to information. The infrastructure became more complex as it adapted to accommodate jurisdictional variations while maintaining a unified global service. The global connection meant that local events could have worldwide impact. Network disruptions, power failures, natural disasters affecting data centers created ripples across the entire infrastructure. The engineering challenge was building systems resilient enough that regional problems didn't cascade into global failures, that redundancy and geographic distribution provided true independence rather than hidden dependencies. Time zones disappeared from the user experience, but remained crucial to infrastructure operation. Maintenance windows had to be scheduled when impact would be minimal, but with global usage, there was never truly quiet time. The infrastructure had to support maintenance and upgrades while continuing to serve queries, requiring sophisticated techniques for draining traffic from systems being serviced and routing it elsewhere. The follow-the-sun pattern of usage created predictable daily cycles, with load shifting between regions as different parts of the world entered and left peak usage hours. Cultural content moderation presented challenges that varied by region. What was considered acceptable content differed across cultures and legal systems. The infrastructure had to support filtering and removal mechanisms that could be applied selectively by region without fragmenting the global index entirely. The technical challenge of maintaining consistency while accommodating local requirements created complex systems of overlays and exceptions. Accessibility varied dramatically based on local internet infrastructure. In regions with high bandwidth and ubiquitous connectivity, search could return rich media results, complex interactive features. In areas with limited connectivity or expensive data plans, the infrastructure had to provide lightweight alternatives, simpler interfaces that minimized data transfer. The global infrastructure supported multiple experience tiers, adapting to local conditions while providing as much functionality as practical. Market competition played out differently in different regions. In some markets, one search provider dominated. In others, multiple providers competed actively, each with significant user bases. The infrastructure had to be efficient enough to compete economically with alternatives, had to provide quality sufficient to retain users who had choices. The competitive dynamics influenced infrastructure investment, driving innovation in regions with strong competition, while potentially leading to underinvestment in markets with less competitive pressure. Geopolitical tensions affected infrastructure development. Concerns about surveillance, about foreign control of critical information infrastructure, about data sovereignty, influenced where data centers could be built, which markets could be served from which locations, which partnerships and relationships were viable. The infrastructure existed in a geopolitical context that imposed constraints beyond the purely technical and economic. Knowledge graphs attempted to encode structured information about entities and their relationships, creating a layer of semantic understanding above the raw text index. This infrastructure required understanding that entities had different names in different languages, different cultural significance in different regions, different relationships that mattered depending on context. Building globally consistent knowledge graphs while respecting local variations required extensive structured data from diverse sources, constantly maintained and updated. Voice search infrastructure brought new challenges around accent and dialect recognition, around understanding spoken queries in noisy environments, around providing results that could be consumed audibly rather than visually. The global distribution of languages, accents, and speaking patterns meant that voice capabilities were uneven, working better for well-represented populations than for linguistic minorities. The infrastructure investment followed usage patterns, creating feedback loops where better voice search in some languages accelerated adoption, increasing the data available for improvement. Mobile infrastructure became crucial as phone-based search exceeded desktop usage globally. The constraints of mobile devices, smaller screens, touch interfaces, more variable connectivity, required different approaches to result presentation and interaction. The infrastructure adapted to serve mobile-first users, with systems optimized for the specific patterns of mobile search behavior, for the geographic and temporal contexts that mobile usage revealed. Emerging markets presented infrastructure challenges around network quality, device capabilities, local language support. Serving these markets required lean implementations that could function on slower networks and less powerful devices, required investment in local language capabilities that might not generate proportional revenue. The business logic of infrastructure investment sometimes conflicted with the goal of universal access, creating tensions between commercial viability and global accessibility. The architecture of search embodied assumptions about knowledge, authority, and truth that weren't always explicit, but shaped how information was accessed and understood. The decision to rank results rather than present them in chronological or random order implied that some information was more relevant, more authoritative, more deserving of attention than other information. This judgment happened algorithmically through calculations based on measurable signals, but the choice of which signals to measure and how to weight them reflected philosophical positions about what made information valuable. The emphasis on popularity as a ranking signal, through link analysis, through click patterns, through usage metrics, suggested a democratic theory of knowledge where collective judgment determined value. Pages that many other pages linked to, results that many users clicked on, content that generated engagement, all received ranking boosts based on these aggregate preferences. This approach had strengths in surfacing genuinely useful resources, but also created potential for information cascades, where early popularity begat more popularity regardless of underlying quality. The tension between objectivity and personalization reflected deeper questions about whether truth was universal or contextual. Personalized results that varied based on user history and characteristics suggested that information needs were individual, that the same query from different users might appropriately receive different results. But personalization also created filter bubbles, where users saw information that confirmed existing beliefs and behaviors, rather than being exposed to different perspectives. The philosophy encoded in personalization decisions shaped users' information diets in ways they might not recognize. Authority, as determined by search algorithms, differed from traditional expertise. Academic credentials, institutional affiliations, journalistic standards, these markers of traditional authority weren't directly visible to ranking algorithms that assessed pages based on links, engagement, and content characteristics. This created both democratization, allowing new voices to reach audiences regardless of traditional credentials, and challenges around misinformation from sources that could achieve high rankings despite lacking expertise or accuracy. The treatment of freshness as a ranking factor embodied assumptions about the relationship between recency and relevance. For some queries, recent information was clearly more valuable. News events, current prices, software documentation. For others, older sources might be more authoritative. Historical information, foundational research, classic literature. The algorithms attempted to determine when freshness mattered, but the judgments weren't always aligned with what individual users needed, sometimes surfacing recent but superficial content over older but more comprehensive resources. The philosophy of comprehensiveness versus selectivity shaped infrastructure decisions. Should search attempt to index everything accessible, or should it be selective about what to include? Comprehensiveness supported serendipitous discovery and reduced editorial bias, but meant including low-quality content alongside high-quality resources. Selectivity could improve average result quality, but required judgments about what deserved inclusion that might reflect biases or limit information access. Different search systems made different choices along this spectrum. Questions about neutrality permeated search philosophy. Could algorithms be truly neutral? Or did any ranking system necessarily embody values and make choices that privilege some information over others? The goal of neutrality was often stated, but achieving it proved elusive. Even seemingly objective signals like link counts reflected the social networks and power structures of who could create links, who had platforms that generated traffic, who operated in environments where link building was possible and valued. The role of commercial incentives created philosophical tensions. Advertising-supported search had to balance serving user information needs against generating revenue from advertisers. The architectural separation between ads and organic results attempted to preserve the integrity of algorithmic ranking while enabling commercial viability. But the existence of commercial incentives created pressure toward results that generated clicks and engagement, which might not always align with results that best answered queries or served long-term user needs. Privacy philosophy varied between providers and evolved over time. The collection of search data enabled personalization and improvement, but created surveillance capabilities and risks of misuse. Different philosophical positions about the appropriate trade-off between utility and privacy led to different infrastructure choices. How long to retain data, what uses were acceptable, how to balance individual privacy against aggregate learning. Users often didn't engage deeply with these philosophical questions, accepting default privacy settings that reflected the provider's philosophy rather than their own considered preferences. The question of who should control search, governments, private companies, non-profits, distributed systems, remained contested. Each model had implications for how search operated, what incentives shaped its development, what recourse users had when it failed or was misused. The dominant model of private operation created concerns about concentration of power, but also enabled investment and innovation at scales that other models struggled to match. The philosophy of control influenced not just ownership, but governance, transparency, accountability. Accessibility as a philosophical commitment meant ensuring that search served users with different abilities, different devices, different connectivity. This required infrastructure investments that might not generate proportional revenue, design choices that prioritized inclusion over efficiency or elegance. The philosophy of universal access sometimes conflicted with business optimization, requiring explicit commitment to serve populations that were costly to reach or generated limited economic value. The treatment of historical information reflected philosophies about cultural memory and forgetting. Should search make everything permanently accessible, or should some information be allowed to fade from easy discoverability? The right to be forgotten, recognized in some jurisdictions, embodied a philosophy that individuals should have some control over their digital traces. But this conflicted with interests in historical preservation, in journalistic archives, in maintaining public accountability for past actions. The role of editorial judgment versus algorithmic determination remained philosophically contested. Some argued that important decisions about information access should involve human judgment, editorial expertise, explicit value choices made by accountable people. Others believed that algorithmic approaches were more scalable, more consistent, less subject to individual bias, even if they embodied systemic biases in their design. The philosophy influenced whether human evaluation supplemented algorithmic ranking and how much weight human judgment received. Transparency about how search worked created philosophical dilemmas. Greater transparency helped users understand results and helped website operators optimize appropriately. But detailed transparency enabled manipulation, allowed those seeking to game rankings to understand exactly what signals to fake. The philosophy of openness had to be balanced against the need to maintain system integrity, leading to selective transparency that revealed general principles while protecting specific implementation details. The question of search as a public good versus a private service shaped expectations and obligations. If search was essential infrastructure comparable to utilities, perhaps it should be regulated or operated as a public service. If it was a private convenience, market competition could discipline providers and users could choose alternatives. The philosophy influenced debates about regulation, about antitrust concerns, about whether search providers had obligations beyond serving their users and shareholders. The temporal philosophy of search influenced how information was weighted across time. Should search privilege the most recent information or give weight to sources that had proven durable across time? Should trending queries receive special treatment, or should search resist amplifying temporary spikes in interest? The answers shaped what information became visible during crucial moments when public attention focused on particular topics, influencing discourse in ways that weren't always intended or understood. The trajectory of search pointed toward increasing integration with other forms of information access and decision support. The boundaries between search, recommendation, navigation, and answer generation were blurring, with systems attempting to understand not just what users queried, but what tasks they were trying to accomplish, what decisions they needed to make, what contexts shaped their information needs. The future seemed to involve more proactive assistance, systems that anticipated needs rather than only responding to explicit queries. Artificial intelligence promised to transform how search understood language and intent. Models trained on vast corpora of text could grasp semantic relationships that purely statistical approaches missed, could understand that questions phrased differently might seek the same information, could generate natural language responses rather than just returning links. The integration of these capabilities would change the nature of search from information retrieval to something more like conversation, where the system could ask clarifying questions, could synthesize information from multiple sources into coherent answers. The challenge of misinformation would likely intensify, requiring new approaches beyond current ranking signals. As content generation became easier and cheaper through automation, as synthetic media became harder to distinguish from authentic documentation, search systems would need better mechanisms for assessing reliability and provenance. The infrastructure for tracking information sources, for identifying coordinated manipulation campaigns, for surfacing diverse perspectives on contested topics, would need to become more sophisticated. Voice and visual search would continue growing in importance, requiring infrastructure that could understand spoken queries in context, that could analyze images to determine what they depicted and what information might be relevant. These modalities brought different interaction patterns, more conversational for voice, more immediate for visual queries, that would influence how results were selected and presented. The infrastructure would need to support multimodal understanding, combining text, speech, and images to grasp user intent. Privacy preservation would become more technically sophisticated, potentially through cryptographic approaches that allowed learning from aggregate patterns without exposing individual queries, or through federated models that kept personal data on devices while still enabling system-wide improvement. The tension between personalization and privacy might be partially resolved through technical innovation, though fundamental trade-offs would remain. The infrastructure would need to evolve to support privacy-preserving computation at scale. Decentralization represented a possible future direction, with distributed search systems that didn't rely on centralized infrastructure controlled by single entities. The technical challenges were substantial, achieving result quality comparable to centralized systems while operating through distributed protocols, maintaining freshness without centralized crawling, preventing spam and manipulation in systems without central authority. But the philosophical appeal of reducing concentration of power over information access could drive continued experimentation with decentralized approaches. Specialization would likely increase, with search systems optimized for particular domains developing alongside general search, medical search, legal search, scientific search. These specialized systems could incorporate domain-specific ranking signals, could understand specialized terminology and concepts, could connect to authoritative databases in ways that general search couldn't. The infrastructure would become more heterogeneous, with different systems serving different needs, rather than a single universal interface to all information. The economics of search might shift as privacy regulation increased, as users became more selective about data sharing, as advertising effectiveness faced challenges from ad blocking and changing user behaviors. Alternative funding models, subscription services, cooperative structures, public funding might become more viable. The infrastructure and its governance could evolve to reflect different economic foundations, potentially changing incentives around data collection and result quality. real-time search capabilities would expand, with better mechanisms for finding and surfacing information about events as they unfolded, for distinguishing emerging information from established knowledge, for tracking how understanding of developing situations evolved. The infrastructure would need to handle more dynamic content, to update indices more rapidly, to assess reliability of information before it had time to accumulate the traditional signals of authority. Personalization would become more nuanced, potentially understanding not just individual preferences, but contextual factors, what the user was trying to accomplish, what their expertise level was, what time constraints they faced. The infrastructure for managing this richer context would require more sophisticated user modeling while respecting privacy boundaries, finding ways to adapt results without requiring users to explicitly configure countless preferences. Accessibility would hopefully improve, with better support for languages and dialects currently underserved, with interfaces adapted for users with various disabilities, with systems that worked reliably on minimal infrastructure in regions with limited connectivity. The expansion of access would require infrastructure investment that might not generate proportional revenue, requiring commitment to serving populations based on access rights rather than purely economic calculations. Regulatory evolution would shape search infrastructure in ways difficult to predict. Requirements around data retention, content moderation, transparency, and competition could mandate architectural changes, could require new systems for auditing and accountability, could influence which services could be combined under single corporate control. The infrastructure would need flexibility to adapt to regulatory requirements that varied by jurisdiction and changed over time. The integration of search with other services might deepen or fragment depending on regulatory and competitive dynamics. Tight integration with email, documents, calendars, and other personal information sources could enable powerful personalization, but raised privacy concerns and competitive questions. The future might see either deeper integration of search into comprehensive personal assistance systems or deliberate separation to reduce data concentration and market power. Quantum computing represented a distant but potentially significant shift in computational capabilities. If quantum computers became practical at scale, they could enable different approaches to indexing and ranking, could break some cryptographic protections while enabling new ones, could change the economics of computation in ways that influenced infrastructure architecture. The timeline remained uncertain, but the potential implications were substantial enough to warrant consideration in long-term planning. The fundamental challenge of matching human information needs to available information would persist regardless of technical advances. Language remained ambiguous, human needs context-dependent, relevance subjective. Better systems could narrow the gap between query and intent, between results and needs, but perfect matching would remain elusive. The future of search would involve continuous refinement rather than ultimate solutions, ongoing adaptation to changing information landscapes and evolving human expectations. The question of whether search would remain primarily a distinct service or become an invisible layer woven throughout other interactions with information remained open. The trajectory suggested increasing integration, with search capabilities embedded in every interface rather than accessed through dedicated search pages. The infrastructure would evolve to support this integration, becoming less visible while remaining essential. Infrastructure that enabled information access without requiring conscious decisions to search. The story of search was far from complete. Each technical advance created new possibilities and new challenges. Each increase in scale revealed problems that hadn't been visible at smaller sizes. Each expansion of access highlighted populations still underserved. The architecture that had emerged over decades would continue evolving, shaped by technical innovation, by economic forces, by regulatory decisions, by the changing needs and expectations of billions of users whose lives had become intertwined with the ability to find information when needed. The future would be written through millions of infrastructure decisions, through choices about what to optimize for and what to sacrifice, through the ongoing negotiation between competing values of access, privacy, quality, and commercial viability. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.